Okay, hello everybody. This is Ryan Smith for Physics 4002 at CSU East Bay, and I will attempt to do a walkthrough of the first homework set. This is the first time that I've done the video, so please bear with me. Our first problem here is, so generally what we're doing is we're looking at permanent polarization that's fixed into a shape, and so that's going to be with something that's a dielectric, right? Not something that is a conductor where the charges are free to move around, but rather where the charges are more or less fixed in their position, but we still have that kind of stretching ability, right? Remember this idea of, you have a positively charged nucleus and your electron cloud can be somehow dragged a little bit to the side in the presence of an electric field. And so if you have all of your atoms that are all pulled to the side a little bit, this is the situation that we're talking about. So the first situation here that we have, I cross this out just because our situation looks a little bit similar here, is that we have a cylinder, and if I look at this kind of from the side on here, I see that I have a permanent polarization that has a constant and then an S-dependence, right? So that's, in other words, that's the kind of vector that's you could think of it as your radial vector, right? In cylindrical coordinates, that's perpendicular to your z-axis. And so as I get larger s, it looks like I have more polarization. So it looks like if I could draw like a big picture, I would say maybe it looks like maybe some we have some kind of polarization with maybe positive charges. Let's see, we're going to do from negative to positive, so we have something like this, and then we have that kind of that shape, sort of minus plus, minus plus, minus plus. But then as we get to further out, it looks like maybe it's stretched more, right? So we have plus, minus, right? So we're going to actually be stretching it out more as we get further out, and this is a symmetrical situation. So anywhere along here, we have plus and minus. Okay, so that's the situation that we have. We're assuming an infinitely long cylinder. And let's review what it is that we're actually trying to do here. So so we've got a Teflon rod, and we are okay. So we have a radius A for this thing here. In a moment, I'll actually move to a fresh sheet here for actually solving the problem. We're supposed to calculate the bound charges. That's both sigma bound and rho bound. And if we recall, sigma is equal to P dot n. Right, that's a capital P, and rho, right, and I'll put a little b there for bound. Rho bound is equal to minus the divergence of P. Okay, so those are the two sort of relevant equations there, and we'll work out the units of this constant, and then we're going to use those bound charges to actually figure out what the electric field is inside. So now we can effectively think, okay, well, we had this polarization. Another perspective on this is to say, okay, well, I have some bound charges. In other words, now I have a separate problem where I forget about the fact that this is even plastic, and I just say, okay, I have this rho, this sigma, and now this is a problem that we've basically done before in 4001. So we'll solve that, and then lastly, we're going to go to the book, and we'll figure out this quantity D, which is the electric field displacement, inside and outside the cylinder, and we'll check to make sure that the equation, namely that this displacement is equal to epsilon naught E plus P. Those are all with vectors. Make sure that that works out, and we'll take a look at the meaning, and we'll discuss that a little bit. Okay. The second problem we have, we're looking at a similar problem, but it's got a hole taken out through the center. So we have kind of this kind of another Teflon rod, but this hole is taken out, and we have an inner diameter B, outer diameter A. Right? Whereas here we just have diameter. I meant to say radius A. So we'll look at, and it also has a different built-in polarization in this case. So we're looking at two different shapes, two different built-in polarizations, and we'll hopefully learn some things along the way. Okay. So those are the problems. And let's see if we can go ahead and solve these. So the the first part here is to figure out what sigma bound is. So my sigma bound is equal to P dotted into the normal vector. Okay, well, the normal vector for my cylindrical geometry, what is that? Well, if I was over here at the edge here, it would be pointing radially outward. So basically, anywhere at that edge there, right? So at S equals to A, there's my A. I want to dot the polarization at that particular location into the normal vector. So that's S hat. So my P is equal to KS in the S hat direction. And I'm dotting that into the normal vector, which is S hat. So it looks like KS, but then remember that this is sigma bound at the surface, right? So this is at S equals to A. So this is equal to KA, okay? So that looks reasonable. So that's our sigma bound, okay? And second, we want to figure out what is the rho bound, or if there is any rho bound. And so I'm just going to use my formula here. Now this is everywhere inside, right? By the way, our P's now, while we're talking about P's in the macroscopic picture of materials, P's are always going to be capital P's. Lowercase, so that's, in other words, the dipole moment per unit volume, right? Whereas the lowercase p was just the dipole moment. So unless we're explicitly mentioning here that we're talking about a singular dipole moment, you can assume that we are talking about indeed the macroscopic polarization of a material. So so I have to use a formula from Griffiths here. I'll just pull out my book here since we're here in real time and we're solving a problem. I'll just show you what I'm looking at. So I'm looking right here at the divergence equation. So you can see that I have a polarization. That's my v vector, right? That's my capital P. It only has an s hat component. There is no phi hat or z hat component. So I'm just looking at this first part here. Okay, and so I'll write that down as minus 1 over s d by ds of s times now the s hat component, which is ks. And if I solve that, it looks like I get a minus 1 over s times 2sk, and it looks like now this s is not an s that's evaluated at any particular place. It's everywhere inside of my my cylinder, but it looks like it actually does cancel in this place. So it looks like I have a kind of frozen in bound charge as a result of this. So basically everywhere uniformly within this kind of cylinder, there's actually this minus 2k. Okay, so we're almost done with part A here. So we've taken a look at the sigma bound and rho bound, but what's this k? Well, okay, maybe one way we could do it is just to say that I know that the units of sigma has to equal to coulombs per meter squared, right? So coulombs per meter squared, and that's going to be, I'm going to say k units of k. I don't know what that is at the moment yet. Times a. Well, a has units of meters, right? So it looks like the units of k is equal to coulombs per meters cubed. Okay. Now let's bring that down here and see if that actually makes sense. Well, I know that rho has to have the units of coulombs per meters cubed, so it works out. I'm satisfied that the units of k is coulombs per meters cubed. Okay, so let's move on to the next part then. Let's see. I wonder how I should do this here. Maybe I'll just start a fresh sheet here for this next part here. It looks like I'm going to have problems once I get down to the bottom of pages, but I'll do my best. So, all right. So for the second part here, we're interested in using these bound charges, namely that basically your sigma b is equal to Ka, and your rho b is equal to minus 2K, where I want to use that information here to calculate the electric field. So it's basically as if we had a separate problem from 4001, where we just had a cylinder that had uniform rho equals to minus 2K, kind of all within inside of here, like this, right? And along the outside, right, I'm just going to kind of draw that as a little shell here to remind ourselves, like, okay, on this outside part here, we have a sigma equals to Ka, right? So that's kind of like a new problem, right? As if you had a bunch of negative charges inside and a thin spherical, spherical, thin cylindrical shell going around the outside that has, how do you say, that has positive charge. Okay. So how can we approach this thing? Well, gosh, we know about Gauss's law. Okay, so Gauss's law tells us that the surface integral, right, over a closed surface of E dot dA, what's that equal to? Oh yeah, it's the charge enclosed over epsilon naught, right? We know that, how that works, right? And this is actually going to be the bound charge, right, in this case, right? So I'm not even going to write that explicitly there, but because those are the charges that we have, are the bound charges, right? There weren't any charges otherwise that we were placing in this problem. So it may well be that there's no net charge, since all we're dealing with is a polarization. But let's see what comes out from the math. Okay? So the first thing that we could do here is to solve for the well, here the left-hand side is going to be the same whether we're outside or inside. But let's solve the outside first. I think it might be simpler. So outside, in other words, S is greater than A. We're going to have a situation where left-hand side is just going to be E times the surface area of a cylinder. Well, unwrap that cylinder, right? So here I've got my cylinder, right? So remember that it's 2 pi s going around, or in this case 2 pi a, and then the distance is L, right? So we have just 2 pi times a times L. And I'm sorry, that's if we were actually at the boundary, but if we're at some imaginary surface, it's 2 pi SL. Okay, that's good. And because remember that this is now a Gaussian surface that's going around the outside, somewhere on the outside, right? And that has a radius of S, some S, right? Whereas this is A here, just to be clear. Okay, so we're outside. This left-hand side here is going to be the same whether we're actually on something that's inside or whether we're outside. It's going to be the same. But let's now calculate the total amount of charge inside. Well, looks like I have a contribution from the sigma and a contribution from the rho. So let's calculate each of those separately. So the sigma is going to be, let's see here. We want to calculate, sigma is the charge per surface area. So apparently if we multiply by the surface area of the cylinder, then we're going to get out what the actual charge is, right? Okay, that seems pretty reasonable. And we're going to add, the next thing that I want to do here is I want to integrate the amount of rho. So in other words, I'm going to do a volume integral of rho bound d tau. Okay, so you could say, I could be very specific here, and I could say d tau prime and rho b of r prime, right? Because we're integrating over charges. But nonetheless, let's see, rho b can come outside of this integral here because, well, it doesn't seem to have any s dependence, right? Or phi or z dependence, right? So let's simplify things here. 1 over epsilon naught. I'm going to replace my sigma b, ka, 2 pi al. Okay. Then let's add minus 2k. And the volume. What's the volume of a cylinder? Well, it looks like it's pi a squared times L. Okay, cool. Let's put it all together. These are looking suspiciously similar. Looks like we've got let me just write them into a kind of a form that looks so we can compare them side by side. This is going to be 2 pi k a squared L. This is going to be minus 2 pi, k a squared L. Oh, they're the same. So that means it's 0. That means, and then remember that this here, right, that this E times 2 pi SL. Okay, well, so just going back to kind of the logic that we had from before in our last quarter, if this expression is 0, well, it has to be true for all S, so that means that my electric field is 0, and we do have a cylindrical symmetry in this case. So E equals to 0. outside. Okay? All right. So in other words, you could think of it as that's another statement of that Q enclosed is 0. Okay, not 0 factorial, but Q enclosed is 0. Okay. So we just solved for the outside case. Why don't we go ahead and do the inside case? So I'll get a fresh sheet of paper for that. Let's see, how should I do this here? I'll just draw a new picture here. So just to remind us that those are our sigma and rho. And basically we're going to have the same thing inside, but let's see. We're going to do E inside, where S is less than A. Okay. And basically, I want to think about this here. Well, okay, here's my cylinder. I'm on a Gaussian surface that's inside, right? Okay, so if that's true, is sigma going to count? Is sigma bound going to count at all? Well, not really, because it's not enclosed, right? So we're not really worried about sigma bound at the moment, right? We're really worried about the rho bound, right? So, so let's try that. Rho bound, basically we're going to have my E times 2 pi SL, and that's going to be 1 over epsilon naught times the Q enclosed. Okay, now the Q enclosed is only going to be the rho contribution at this point. So let's calculate that. Then I said that rho can come outside the integral, but I'm going to just still kind of redo some of the steps anyway because it'll help us in the next part. I'm going to do a volume integral. That's a triple integral here. Rho sub b of r prime, d tau prime. Okay. And I'm going to be bringing that guy outside, so I have minus 2k over epsilon naught times my volume. And my volume of integral of d tau is going to be pi, not a squared, but s squared, right? Because this is here's my center, right? So I'm going to s, right? Whereas this was a in this case, right? So now my s is less than a, right? So I'm only including as much charge as is enclosed in this area here, right? I'm not including the charge of the whole thing. So this is a classic, this is one of the, the crux, of the thinking part of this question is when you get to this step, you really need to stop and think about, okay, what am I integrating over? I could have said the volume of the Gaussian surface or something like this, to really, something like that, through volume that's enclosed by S or something like this, right? To really, really remind myself, in other words, this is an integral from 0 to S, and then from 0 to 2 pi, and from 0 to L, right? And then S, ds, d phi, dz, right? So that kind of level of thinking through things, right? So dz. Okay, so this thing here, we're almost done. E times 2 pi SL. I'm going to cancel out a 2 and a pi, and it looks like I get to cancel out an L, and I get to cancel out one of the S's here. So in other words, E, which I know is in the sort of radial direction, or the S hat direction, is going to be equal to minus Ks over epsilon naught. I'm just wondering if I might have missed any factor of 2. No, I don't think so. S hat. Okay. And this is my E in. This is my E inside of this thing here. So, okay, cool. So it looks like, if I go back and kind of look at the answer outside, it looks like I had 0 outside. And let's see, I'm going back to the original question right now to make sure that I handled everything. So it looks like there's like a kind of situation here where you have a linearly increasing electric field, and then it suddenly, like when you get actually to that A point here, it drops down to 0, and it kind of continues on like that. So E and S. Okay, so basically that's not that exciting, but that's kind of what's going on. Okay, so that is our electric field. Okay. Okay. Now why don't we take a look at the part C? Let's see here. Did we do everything here? Fine. E inside and outside the cylinder. Okay, we found the magnitude and we found the direction. So it looks like actually the electric field sort of points inward, right? Which is, I mean, surprising, and I wasn't expecting it, but kind of makes sense if you have more charges that are kind of laying around the outside of things. Like, so if I just kind of make this a really, really simplified picture here, right? And I just say kind of this a bunch of negative charges kind of closer to the inside. Well, yeah, I guess I would kind of expect that the electric field sort of points inward here, right? Not outward. So I guess it sort of makes sense somehow. And I made a mistake here. This is the absolute value of E, right? So it actually does point negative, right? So I just plotted the magnitude here. All right, so the last part is we got to deal with this D thing. So what's D? Well, let's go to the next page. Okay. So Griffiths, in equation 4.21. So let's see, I'll bring this guy here. So Griffiths equation 4.21 says that D equals to epsilon naught E plus P. And by the time you're watching this, we will have already worked this out carefully in class. Okay, and so what are we supposed to do? We want to find the electric displacement inside and out using the fundamental definition. So if D is defined this way, well, let's just add things together. So it's pretty easy outside, right? We already figured out what E was. Remember? It was 0, right? Why? Because we had no charge enclosed, right? So we have 0. And what's the polarization outside? Well, there can't be any polarization outside because there's no matter, right? So 0, right? So D outside is 0, right? It's kind of an easy result. Okay, now inside, maybe there's something more interesting happening. D inside, well, we're going to have to add some stuff here. So I got to look back to my solution. Hopefully you've got this copied onto your paper as well. I have minus ks over epsilon naught s hat. And then I have this epsilon naught here, so I'm going to write epsilon naught. And then I'm going to add the polarization, which I know to be ks in the s hat direction. So I'm going to look at this here, and I'll say, okay, well, epsilon, epsilon, minus ks plus ks in the s hat direction, and that's equal to 0. Cool. All right. So, what do we want to say here? Well, there's no D. Okay. Why is there no D? Well, let's just look to the book for a moment, because it's going to help us to make a little bit more sense of this result. Okay. All right, cool. So this is where I want to look right now, is this electric displacement. When we have situations of symmetry, we can actually say that the D can be calculated from just in considering the free charges that are enclosed. And, well, according to the definition of this problem, there are not any free charges, right? So the free, what does it mean, free charges? Is the stuff that we control. In other words, the stuff that's not related to the actual polarization, right? So all the charges that we were dealing with are so-called bound charges, and that's kind of encoded into P. But notice how when D is 0, then P and E are essentially just related to each other by that constant epsilon naught, right? So they're basically opposites of each other. So I think that's a really nice way to kind of summarize and see how things are connected to each other. Gosh, I think I got everything. So yeah, so well, that's hopefully a pretty thorough treatment of this situation here. There's no free charges, and so that's why things are working out for us. Okay, so that concludes the first part here, and I'll go ahead and stop and start another video for the second one.